Dawn, July 2nd, 1937. Somewhere over the middle of the Pacific Ocean, a woman is gripping the controls of a plane running on fumes. Her voice crackles through a radio. "We must be on you, but cannot see you. Gas is running low." Below her, nothing but open water in every direction. She was less than 2 hours from completing one of the greatest achievements in aviation history. Instead, she was about to vanish forever. Who was Amelia Earhart, and what was she attempting? Amelia Earhart wasn't just famous. By 1937, she was arguably the most recognized woman on the planet. In 1928, she became the first woman to cross the Atlantic Ocean by plane. Though she was a passenger, not the pilot, that distinction gnawed at her. She told reporters afterward that she had been nothing more than a sack of potatoes. So in 1932, she went back and flew the Atlantic alone, through storms, mechanical failures, and near disaster, landing in a muddy field in Northern Ireland with grease-covered hands and a grin on her face. But even that wasn't enough. Her next goal was the longest, most dangerous circumnavigation ever attempted, a flight around the entire globe, hugging as close to the equator as possible. Every previous around-the-world flight had stayed near the northern latitudes, where land masses cluster together and emergency landings are possible. Earhart's route would cross the widest, most remote stretches of open ocean on Earth. The final and most critical leg of the journey, the one that would make or break the mission, was a 4,000-kilometer hop across the central Pacific from Lae, New Guinea, to a dot of land so small that calling it an island feels generous. The island, Howland Island, and why it mattered. Pull up a map of the Pacific Ocean and stare at it for a while. Notice how there's almost nothing there. Millions of square kilometers of water, almost no land at all. Now zoom in to the dead center of that map. There it is. A sliver of coral and scrubby grass barely 2 kilometers long and less than 1 kilometer wide. Howland Island. Population at the time of Earhart's flight. A handful of young colonists placed there by the US government to establish territorial presence. If Earhart's Lockheed Electra, a twin-engine, propeller-driven aircraft she had converted into essentially a flying fuel tank, couldn't make it to Howland, there was nowhere else to go. The nearest alternative landing strip was over 1,000 kilometers away. To even attempt this crossing, Earhart stripped the Electra down to bare essentials. Out went insulation, passenger seats, anything that added weight. In went additional fuel tanks, lining the interior of the fuselage like a pressurized bomb. The engine noise without insulation was so thunderous, she and her navigator had to communicate using handwritten notes passed back and forth. She estimated the Electra could fly somewhere between 6,600 and 7,200 kilometers on a full tank of fuel, in ideal conditions. The distance from Lae to Howland was right at the edge of that range. There was no margin for error. There was also no margin for missing the island. The navigator, Fred Noonan, and the art of finding your position. Over open water. Flying with Earhart was Fred Noonan, one of the most experienced aerial navigators of his era. His job was to answer one deceptively simple question at all times. Where are we? Over open ocean in 1937, that question had exactly 2 practical answers. The first was dead reckoning. Noonan knew their compass heading, their airspeed, and the predicted wind speed. From those 3 numbers, He could calculate their ground speed and estimate how long it should take to reach any given point. The technique is called dead reckoning because you're reckoning your position forward from the last confirmed fix, step by step, calculation by calculation, and any error compounds over time like interest on a debt. The second method was celestial navigation. Noonan carried a thick almanac listing 58 navigational stars and the exact point on Earth's surface. Each one would be directly overhead at any given moment. By measuring the angle between a star and the horizon using a sextant, he could calculate how far away they were from that point. Do this for 2 stars, and you get 2 enormous circles on the globe's surface. Where those circles intersected, that was their position, in theory. In practice, both methods accumulated small errors over the course of an 18-hour flight. And with a target as tiny as Howland Island, small errors were the difference between a triumphant landing and disappearing into the sea. That's why Earhart also brought a third tool: radio. The radio plan, a web of antennas and frequencies. Earhart's Electra was equipped with 5 separate radio antennas, each serving a different purpose. Understanding them is the key to understanding why she disappeared. The largest was a trailing wire antenna, 76 meters long, that could be reeled out behind the plane like a fishing line during flight. This was used to transmit and receive Morse code on low frequencies, around 400 to 500 kilohertz, the standard communication band for ships and remote stations. Low frequencies like these have wavelengths of hundreds of meters, which meant the antenna needed to be physically large to interact with them efficiently. Earhart's trailing wire, though only about 1/8 of the optimal wavelength, was connected to a powerful transmitter, so it worked well enough over long distances. Then there were 2 antennas for voice communications on higher frequencies. A V-shaped transmitting antenna sat on top of the fuselage, while a receiving antenna ran along the aircraft's belly. Higher frequencies are useful because they require smaller antennas, critical on a stripped-down aircraft, and because they can travel enormous distances by bouncing off a layer of the upper atmosphere called the ionosphere. Starting about 50 kilometers above Earth's surface, intense solar radiation strips electrons off gas molecules, creating a belt of charged particles. Radio waves at certain frequencies interact with these free electrons and get reflected back down to Earth. This bouncing effect, called skipping, allows signals to travel thousands of kilometers, ricocheting between the ionosphere and the ocean's surface, like a stone skipping across water. But skipping has a critical weakness. It scatters signals in unpredictable directions. A skipping signal arrives from multiple angles simultaneously, which makes it impossible to determine the direction it came from. You can hear it clearly, but you can't tell which way to point the plane to find it. The fifth and most important set of antennas was the direction-finding system, a loop antenna and a sense antenna working together. This was Earhart's ace in the hole. The loop antenna could be rotated until the incoming signal reached its minimum, a null, and the direction of that null told the pilot exactly which way the transmitter was. The sense antenna complemented it by identifying whether the signal source was in front of or behind the plane. This system worked beautifully, but only for lower frequencies that didn't skip. For it to guide her to Howland Island, the ships stationed along her route needed to transmit on the right frequency. And that's where the chain of catastrophic misunderstandings began. The ships, a Coast Guard flotilla in the middle of nowhere. The US government had positioned 3 vessels along Earhart's route. The USS Ontario sat roughly halfway between Leigh and Howland. The USCGC Itasca was anchored just offshore from Howland Island itself, its job being to guide Earhart in during the final, most critical portion of her approach. A third ship, the Swan, was stationed between Howland and Hawaii. The Itasca was the most important. Its crew would send out radio signals that Earhart could home in on, and it was equipped with radio direction finding gear to help locate her if necessary. There was just one problem. Earhart and the Itasca were not on the same page about almost anything. The confusion began with time zones. Earhart was logging flight time using Greenwich Civil Time, the standard reference for navigation. The Itasca crew was operating on their local ship time, which was 11.5 hours behind Greenwich. Meanwhile, Howland Island itself used Hawaii time, 10.5 hours behind Greenwich. 3 parties attempting a rendezvous on a tiny island in the middle of the ocean were each working from a different clock. This meant that when Earhart said she would transmit on the half hour, the Itasca crew misinterpreted which half hour she meant. When she listened for them, they were transmitting. When they listened for her, she was transmitting. They kept missing each other like 2 people on opposite sides of a revolving door. But the deeper problem was the frequency, the critical mistake. Wrong numbers, fatal consequences. Before taking off, Earhart consulted a radio expert in Leigh about what frequency the Itasca should use to transmit Morse code that she could home in on with her loop antenna. The expert recommended 750 meters wavelength, which translates to approximately 400 kilohertz. That was well within the range where her direction-finding loop worked perfectly. Here's where the fatal mistake happened. In 1937, radio operators often described signals by their wavelength in meters rather than their frequency in kilohertz. The 2 numbers measure the same thing from different directions. Wavelength gets shorter as frequency gets higher. Earhart, who was not a trained radio operator, confused the units. When she relayed the plan to the Itasca, she requested they transmit on 7,500 kilohertz, not 750 meters. 7,500 kilohertz is a very high frequency. Its signals skip wildly off the ionosphere. They cannot be direction found. She had asked for exactly the frequency that would make her navigation system useless. And when she specified this frequency, she added a note. If this frequency is unsuitable, please inform me. Nobody corrected her. The Itasca's commander, aware that her loop antenna had limitations, but unsure whose responsibility it was to intervene, said nothing. The Coast Guard's San Francisco division tried to push the Itasca to take more direct responsibility for Earhart's radio setup, but was rebuffed. Each party assumed someone else would catch the error. Nobody did. The final hours. Circling. Running out of time. At 6:15 in the morning, Howland Island time, the Itasca's radio operators heard Earhart's voice clearly. She was about 200 miles out, needed them to take a bearing on her signal so she could home in. The radiomen were baffled. They had expected to help her navigate, not the other way around. And even if they'd wanted to take a bearing on her voice transmission, they couldn't. Voice signals at high frequency skip and scatter. There's no null to find, no direction to calculate. Her signal was arriving from everywhere and nowhere simultaneously. Earhart heard only static in response. She had a second problem. Somewhere along the route, possibly during takeoff, possibly during flight, her belly-mounted receiving antenna had stopped working. She could transmit, but she couldn't hear the Itasca's responses. She was shouting into the dark, unable to hear anyone shouting back. At 7:42 a.m., her voice burst through the Itasca's speakers so loudly that crew members ran above deck, convinced she must be close enough to see. She said she couldn't spot them, that fuel was critically low, that she was flying at 1,000 feet. The Itasca began transmitting A's in Morse code on 7,500 kilohertz, the frequency she had requested. In the cockpit, Earhart heard the stutter of dashes filling the cabin. She seized her direction-finding loop and began rotating it, searching for the null. But the signal never dropped out. No matter how she turned the loop, the signal seemed equally strong from every direction. The high-frequency waves were bouncing off the ionosphere and arriving from dozens of reflected paths at once. There was no clean null to find. She transmitted frantically. "We received your signals, but unable to get a minimum. Please take a bearing on us and answer with voice." The Itasca tried to explain that her voice frequency was too high for them to take a bearing. She almost certainly never heard this response. Her receiving antenna was gone. At 8:43 a.m., in what would become one of the most haunting radio transmissions in aviation history, Earhart's voice came through one final time. She said she and Noonan were flying a north-south line, searching for the island. She sounded, witnesses said, on the edge of tears. That was the last anyone ever heard from her. What happened, and what could have saved her? The search that followed was the largest and most expensive in American history to that point. 16 Navy and Coast Guard vessels and 65 aircraft swept the ocean for over 2 weeks at a cost of approximately $4 million, close to $90 million in today's money. They found nothing, not a piece of wreckage, not a life jacket, not a trace. The evidence overwhelmingly points to a straightforward conclusion. The Electra ran out of fuel somewhere within reach of Howland Island and went down at sea. What's remarkable, and what makes this story so hard to let go of, is how many different things could have changed the outcome. If the trailing wire antenna had been kept on the plane, Earhart could have transmitted on low frequencies that the Itasca could direction find. She removed it because it was only useful for Morse code, and neither she nor Noonan were proficient in Morse. But proficiency was exactly what the mission required. If the unit confusion over 750 meters versus 7,500 kilohertz had been caught by anyone, Earhart would have specified the correct low frequency for the Itasca to transmit. Her loop antenna would have found a clean null, and she would have flown directly to the island. If Earhart's receiving antenna had been functional, she would have heard the Itasca's responses and understood the communications breakdown in time to fix it. And there is one more thing: the switch mentioned at the start of this story. Earhart's loop antenna could receive signals on a wide range of frequencies, even if it could only direction find on lower ones. If she had simply switched to using her loop antenna for all incoming communications, rather than relying on the broken belly antenna, she would have been able to hear the Itasca's voice transmissions. Once she could hear them, they could have coordinated on the correct frequency, guided her with a proper low-frequency signal, and brought her safely down. That switch, that single small adjustment, might have changed everything. The bigger lesson: knowledge and responsibility. When you dig into the Earhart case expecting to find the story of a doomed mission, a woman who simply pushed too far, into conditions too brutal for anyone to survive, you find the opposite. You find a cascade of small, fixable problems. You find a highly competent woman who lacked detailed knowledge of the radio systems she was depending on. You find a crew of trained radio operators who had that knowledge but didn't take responsibility for sharing it. You find bureaucratic diffusion of responsibility, where each party assumed someone else was handling the critical details. Earhart didn't fail because the Pacific Ocean was too vast. She failed because the chain of people responsible for her safety broke down at every link, and because the physics of radio waves, invisible, silent, governed by mathematics she hadn't fully mastered, betrayed her at the worst possible moment. The ocean didn't swallow Amelia Earhart. A misunderstood unit conversion did. A malfunctioning antenna did. A commander who didn't speak up when he should have did. Understanding how things work, really understanding them at the level where you know the difference between 750 meters and 7,500 kilohertz matters. It matters the way oxygen matters. And when someone else has that knowledge and you don't, you are entirely dependent on them being willing to take responsibility for what they know. In the silence over the Pacific, nobody did. And that silence has lasted for nearly 90 years. If you found this story fascinating, consider what other mysteries of the 20th century hinge on misunderstood physics and failed communication. And hit subscribe, because we're just getting started.